All right, kids, let's try this. Here we go. I'm gonna hide that. All right, electron configurations and orbital diagrams. The electron configuration is the organization of electrons. It's giving you a unique address for each electron, basically. Here's the format it's in. It's going to have a energy level designation here in green, a sublevel, so sort of where in that energy level the electron is, that would be the sublevel, and then it's going to tell you the number of electrons in that sublevel as a superscript. So remember, the energy level is, this would be the first energy level, this would be the second energy level, this would be the third energy level. So it's sort of like the energy level, you know, how far it is. There's these nodes in between the probability cloud, and it's getting further and further away. So there's more and more room for more and more sublevels, the bigger the energy level, because there's more distance to the nucleus and hence more room to put those electrons into different sublevels. All right, that was clear in my head. Here are some examples. So boron is 1s2, 2s2, 2p6, 2p1. How many electrons are there? We would add these electrons here, 2 plus 2 plus 1. So it's a total of 5. And the atomic number for boron is 5 if you look on your periodic table. So that's 5. And your atomic number is the same protons as electrons in a neutral atom. Now, if we have this one, 1s2, 2s2, 2p6, how many electrons are present in this atom of neon? So you should be adding these superscripts that tell you the number of electrons. These numbers in front are telling you the ring or the energy level, and these are just telling you the sublevel. So 2 plus 2 plus 6 is a total of 10 electrons. And lo and behold, if you recognize that as a 10, it's a Halloween 10. It's scary. I should have done it in orange. Woo! All right. That's the atomic number for neon. It has as many protons as electrons because it's a neutral atom. Awesome. All right. So the Aufbau, I believe that's how you say it, principle, it's electrons will occupy the lower energy regions first before moving upward. So here is a diagram of energy levels, and you can see this works out that you fill up the first energy level, the second energy level, and the third energy level is where it starts falling apart. You get the 3s and the 3p, and rather than fill up the 3d, you actually fill up the 4s first. And that makes people a little upset. And then look, even with the Fs, you don't fill the 4F until you've already gotten into the 5S and 5P. And people tell me, what the what, Mr. Roach? Why is that the case? Well, electrons aren't doing it to spite you. Electrons aren't intelligent. They're just doing what energy tells them to do. And this is basically telling you that they do whatever the lowest energy thing is. So think of it as if you pour sand should fall down to the lowest position, right? Gravity pulls on sand, and if you're pouring sand out, it should go to the lowest position. But look here, I poured sand in a funnel. Here was the first position, the second position, the third position. And as you can see, there's some sand that hasn't gotten filled up to the fourth position, and yet some other sand is almost at the sixth height level. So what's going on, sand? What'd you do that for? And it's just because sand was doing what sand does. It's going to the energy level that's lowest. And sometimes it's easier to be a little higher than lower. All right. So we're again looking at these energy levels like the Bohr model. And so the first one is the smallest. So there's only going to be room for one sublevel, 1s. The second energy level has room for a little bit more, the 2s and the 2p. The third energy level has room for even more, 3s, 3p, and 3d. But you notice here the 3d doesn't fill up before the 4s. The 4s, the fourth energy level, fills up a little bit before the 3d. Then it goes to 4p, and the same pattern happens there. You need to know this order of energy levels. And that's when initially you all yelled at me, and now you're getting better at it. But let's take a look here. Another way to look at this, by the way, is like, why 4S before 3D, right? When you're filling up a theater, and my daughter made this, and that's why I like it. You don't always fill up the whole first row before people start going in the second row, and you don't fill up the whole second row before people start getting in the third row, right? People sort of just go into rows whether they're filled all the way up or not. Think of it that way too, if that helps. All right. So how to remember these things, how to remember the order. You can make this chart, and this chart I don't love, but last year loved. And you just start with 1s and you go down all the way down to 7s for the first row. And since you remember that the 1 only has room for an S, there is no P in the first one because it's not big enough. So 2P can't go in the 1 area. It goes in the 2 area. Where did my little pointer go? My pointer's gone. Oh, well, we will live on. Oh, there it is. Nope, there it's gone. Oh, there it is. Okay. So 2P starts here. There's no 1P. So it's 2P, 3P all the way down. Then 3D. Think of the movies, right? You see things in 3D. There is no 2D because it's not big enough. The 3D is big enough to hold a D suborbital sub level. So 3D, 4D, 5D, 6D. And then F, again, the 3 energy level is not big enough to hold enough. It has to go to the 4, 4F, 5F. Then you draw these diagonal lines, and these lines tell you what goes first. So first you fill the 1S, then you fill the 2S, then you fill the 2P, then you fill the 3S, then you fill the 3P, then you fill the 4S, then you fill the 3D, the 4P, the 5S. This works. The problem is it doesn't tell you how many electrons go into each. And it also, if you draw it wrong, you get everything messed up. I prefer this way here, where basically the row you're in tells you what you're filling. And you remember that there is a 1S. This is the S area here. And you'll remember there's always 2 electrons that go in the S because there's only 2 things in the S area. This is the P area here. And you'll remember there are 6 electrons that go there because it's 1, 2, 3, 4, 5, 6 elements in there. This is the D area, and you'll remember there's 10 electrons that go in there because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements across the D area. And this is the F area down here, and you'll remember it's 14 that go in there because there's 14 elements across here. I'm not going to count again. Count for yourself after pausing the video if you'd like. All right, so the only trick with this is the row you're in is the energy level you're in. So row 1 is the 1 energy level, 1S. Row 2 is the 2nd energy level, 2S, 2P. That works until you get to the D, because remember, we don't fill in the D until we've already filled in the S. And the elements are trying to tell you that if you do this in numerical order, right? 17, 18, 19 is in the S. It's in the 4S area. So you fill up the 4S before you fill up what you would want to call the 3 or 4D, but it's not. It's the row -1 for the D block. So the D block is always whatever period it's in, whatever row it's in, which in this case is 4 -1. So this is the 3D, this is the 4D, this is the 5D. And down here, it's that rule -2. This is where the first ones fill up, the F's. So the lanthanides fill up in there. So you're in row 6. So you're filling up the 4F first, and then you're in row 7. So let's take a look at how to do this. You've played Chutes and Ladders, right? And you have no problem going 1, 2, 3 in order of the numbers. There's ladders, there's chutes. Let's ignore that for a minute. The point is you go in order of numbers, right? You go to 1, you go to 2, you go to 3, whatever. So the same thing works here. If you start here, and I say, what is, and here's the S block, by the way. So the S block is pink, the D block is green, and the P block is yellow. And I'm telling you, what is beryllium? So you'd say, okay, how do I get to beryllium? I have to go through the S region, 1, 2, and then 3 and 4. That's what I'm going to do. So 1, 2, that was the 1S box, and I did it twice. So it's 1S2. Right, so it's 1S2. I'm gonna draw it. No, you're not. That didn't come out so bad. But I'm not there yet, right? So I got to go 2 more, 3, 4. I went into row 2, so that's the 2nd energy level. And I'm still in the S block, so that's S. And I had to go twice. So the answer for beryllium is 1S2, 2S2. And you say that's all fine and dandy, Mr. Roach, but what about aluminum? All right. So to get to aluminum, we start here again. So let's go back. We're starting here again. And we had to go 1S2. Had to go 2 S block, 2. And now what's next? After 4 comes 5. So this is the P block, you may recall. And the P block in the 2nd row. So this is the 2P. So now we're up to 2P, 2P. And we're trying to get to aluminum, which is way down here. So we got to go a lot through the 2P. 1, 2, 3, 4, 5, 6. All through the 2P. So 2P6. And now we're at number 10. We got to go to number 11, which is down here. So we're in row 3. So we're in the 3 energy level. And we're in the S block. So 3S. And we got to do that twice. We're trying to get here to aluminum. So it's 3s2. 2 electrons needed to get there. And now we're in the p block in row 3. So it's 3p, 3p. And we have to do it once. Bam. So it's 3p1. Does that make sense? So then if I asked you to do something like titanium, right down here, titanium, you'd have to go, so we start at the beginning again, all the way back here, and you're in the S block, 1s, and you do that twice. You're in the S block, second row, 2s, do that twice. In the P block, number 5, you got to get through all those. So P6, 2p6. In the S block again, row 3, so 3s, 1, 2, 3s2. You're in the P block, row 3, so it's 3p. This time it's going to be 6, right? We had to, because we're trying to get here to titanium, so it's 3p6. 6. All right. And then we're in row 4 in the S block, so it's the 4th energy level, the S sublevel, and we're going to need to go through that twice. So it's 4s2. We're still not at titanium. We're getting there. And then 2 more, right? So this is now the D block. And you may recall that I told you that it's the row you're in -1. So it's 4 -1. It's in the 3 3 energy level. And that's a 3. And you got to go twice to get there. 1, 2. So it's 3d2. This is going to work for most anything. I'll show you the ones it doesn't. But basically, you just do like this, right? So if we are going all the way to urbidium, you have to do the 4s and then the 3d, and it's 10. You can see here 10x is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would be 3d10. Then 4p, 1, 2, 3, 4, 5, 6. Then 5s, 1, 2, and then row -1, so 4d1. And then this here, if we head back to indium, that would be row 5p. So 5p, 1, 2, 3, or whatever you need to do there. All right, hopefully that helps walk you through those. So you don't have to memorize all that craziness, and I can't jump back.
Okay, so if we're looking at this, you'll notice that the electron configurations always kind of start the same, and it gets a little repetitive, right? You're always starting everything with 1s2. And then after that, you're starting everything with 2s2, right? And then after that, you're starting everything with 2p6. And then after that, you're starting everything with 3s2. Wouldn't there be a nice way to write this in shorthand? And what we do now, there are certain groups on the periodic table, we'll get to that a little later, but you notice this one here, the noble gases, noble, right? The royalty of the periodic table. Everything on the periodic table wants to be like a noble gas. And since we don't really have nobility anymore, it seems to work when I tell people everything on the periodic table wants to be like a Kardashian. And that's sort of the Kardashian row. Okay, so everything in that row, the noble gas row, is considered sort of a Kardashian on the periodic table. For some reason, all the elements want to be like them. So when we're doing these electron configurations, what we can do is, for shorthand, we can take these Kardashians and use them as their status and replace everything. So if you want to replace 1s2, you can replace it by just writing helium in parentheses like that, in brackets. If you want to replace 1s2, 2s2, 2p6, you can replace that by just writing neon in brackets. You can replace 1s2, 2s2, 2p6, 3s2, 3p6 by putting argon in brackets. Okay, so all of these noble gases can do that. So since argon is 1s2, 2s2, 2p6, 3s2, 3p6, you can replace all of this in titanium with argon because it's a noble gas, and then you only have to write this much. You see how that works? So it's a shorthand. You don't have to do it this way, but it helps you understand how important those noble gases are. So if we're doing zinc, okay, if we take a look at what zinc is on the periodic table, zinc is number 30. So it's going to be everything that argon is, right? Which is number 18. And then starting with number 19, then potassium, we're going to do 4s2, okay? and that gets us through potassium and then calcium, and then we got to get to zinc, which is at the end of the D block. Since we're in the D block, we're going to use 3 because we go 1 down from the row we're in, and it's D10. So it's everything argon is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, 3d10. Okay, so lead, I don't know lead off the top of my head, so let's take a look at lead real quick. Lead is number 82. So lead is going to be everything that xenon was, which is number 54. Okay, so lead's going to be everything xenon was, which is number 54, and then start up with 6. So lead is going to be, all right, everything xenon is. And then we're in row 6, so it's 6s2. And then we actually get into the F. And you won't ever need to know this for anything until you get really deep into chemistry, but that's going to be 4. It's 2 below the row you're in. And there's 14 in the F. And then I'm going to need to get through the D, which is 5. So it's 5D10, I think. Where was lead? Yeah, so lead is 2 over in the S. So yeah, so then we're going to get through all the 10, 3D10, and then 6S, 6P rather, 6P2. Because if you look at where lead is, right, so lead is everything xenon is. It's 6S2. This is telling us go down here, so it's 4F14. And then it comes back here for 6 minus 1 is 5D10, and then 6P2. So I'll never let you do an F1 because those are crazy and they start doing some funky stuff. But just to understand how that the shorthand helps, because then you don't have to keep writing the same thing over and over again. So if you like to use, here's with argon, right? All of these are using argon in the shorthand, and argon stands for 1s2, 2s2, 2p6, 3s2, 3p6. So you can do that if you want. You don't have